Hi, sir.
Hi, Amy. How are you doing?
I'm good. How are you?
Good. How are you doing? Long time.
Yeah, it feels so long. Um, yeah, all right. Just still practicing, watching your videos, doing questions.
That's
So,
great. So you're able to understand curve sketching and concepts behind it?
yeah, I'm actually kind of getting it. I'm quite surprised. I think definitely doing the polynomials and stuff is definitely helping here. It's just a few other, like the local minimum stuff. So I've got the whole graph. That's quite cool.
That's very good. So how do you find GCSE level A curriculum matching with what I'm teaching? Are you able to do questions from your book?
I haven't attempted them yet.
Okay.
Just doing all your videos, but I get your videos. I don't know if that's the same
Okay.
level as my book. Yeah.
Fine. So after today's lesson, I'll request you to do all the questions from your book on
Okay.
calculus, right? So,
Mhm.
and then share with me whatever you're not understood. So we can cover up on those topics, and all the concepts should be clear to you. We still have to do the chain rule and the implicit derivation, but I hope with the introduction to how to calculate derivatives using power rule, quotient rule, and the product rule, and also understanding first derivative and second derivative, you should be in a position to actually solve most of your questions, correct?
All right. Okay.
Right. So we still have to go for 2, 3 more units, which include finding derivatives using chain rule, implicit differentiation, and some applications on rate of change and optimization. So those are big things, but still at this stage, you can give an attempt and see how much have you really understood, right? Share with me the questions which you find difficult or wherever you need help. Okay.
Okay.
So today's lesson will actually focus on how to sketch proper graph, right? So excellent graphs we can sketch using the techniques which we have learned. So now, uh, let us say if we have a polynomial, what do you think? How should you be going about in sketching a graph of a polynomial? Can you just give me in short, what do you think about it?
So would you start with looking at the degree? So that would tell us whether it's the same end or opposite ends. Look at the zeros. So that would tell us about the behavior of the curve. You would look at Y-intercept by plotting x as 0 into the function.
Yes.
And now we did about finding the derivative to find the local max and min.
Yes.
And you can do the second derivative to find the concavity, but
Perfect.
it's not really necessary.
Perfect.
Yeah.
That is exactly what we are going to practice. You have very good foundation. There couldn't have been a better answer. Let me now share with you the screen, and then we'll actually discuss in details how should we go about. Okay, can you see my screen now?
Yeah.
Okay, so we'll learn about curve sketching. We'll begin with the algorithm for curve sketching, and we'll take up 3 examples. One of them will be based on polynomials, the next one will be on rational functions, and then we'll take up radical function. And then I'll provide rather some simple practice test questions for you, which could be beneficial for any exam preparation. Okay? So we'll begin with the polynomial graph, that is the simplest of all. So here is example number 1. You need to sketch graph of f of x equals to x plus 1 times x minus 2 whole square. Now here are a few questions for you to answer before even you begin graphing. So first one is, you can start answering me the questions as I ask you. What is the domain of the function? The
Oh, this
polynomial
one.
given to you. All real numbers. What is the
Yeah.
range of the function?
All real numbers. Y belongs to all
Yes,
real
all
numbers.
real numbers. What is the y-intercept of this particular function?
0, 4.
Okay, so you'll substitute 0 and calculate. That was a good calculation. 0, 4. Yes. How many x-intercepts will the function have?
2.
2. Very good. Can any of these x-intercepts be local extrema?
So they're no.
The function is x plus 1 times x minus 2 whole square. Okay, so we'll pass for this. What is the difference between zeros and x-intercept?
So x-intercept, we all know, is like where it crosses the x-axis, but zero is like, you always say, gives a little bit more information. So it will tell you about the order or the multiplicity or like the behavior of the curve.
Behavior. So let's get back to a function. F of x is x plus 1 times x minus 2 whole square. How many zeros will it have?
2.
2. Can you tell me the order and multiplicity of these zeros?
Yeah, so at x equals minus 1, it would be a linear, and then at x equals 2, it would be a quadratic. Like
so does it have a turning point at x equals to 2?
Yeah.
And
so that is a local
extrema. We are not
GCSE.
sure whether it is maximum minimum, but that's the local extrema. Do you see that?
Oh, yeah.
So when you look at the polynomials with your brilliant knowledge and grasping of this subject, I think just by looking, you should get the graph in your mind, right? You also understand the end behavior. So what is the end behavior of this particular function? Can you tell me that?
So the degree is 3.
Yeah.
So it would be on opposite ends. So we'll go from quadrant 3 to 1. And we know that because the leading coefficient is 1. So that means the right-hand side is up.
Yes. Positive leading coefficient, right side up. Yes.
Yeah, so quadrant 3 to 1.
Okay. So if you look into the zeros, minus 1 is on the left side and 2 is on the right side. So it will start from quadrant 3, hit minus 1, go across above the x-axis, come back and return, and then bounces back from 2, right? So we have a local minimum at 2. Does it make sense?
Yeah.
So you have answer that has a local minimum specifically at the x-intercept 2. And that is the beauty of zeros. Zeros has this hidden information about the behavior of the curve at the x-intercept, right? So we know it was a linear, it will go across. The other one is quadratic in nature, degree 2, it will bounce back. So it is the turning point, and every turning point will lead to some local extrema. Perfect? Okay. We have also talked about question number 8, which is end behavior. Question number 9 is, how many points of inflection do you expect for this function?
1.
Why?
Because, so the degree is 3, right?
Good.
So if that's a cubic, we talked about every cubic function has at least, or we will only have 1 point of inflection.
Perfect. Can you tell me the value in general of that point of inflection if my equation is ax cubed plus bx squared plus cx plus d?
So like x equals minus b over 3a?
Perfect. 3a. That is absolutely correct. That is the only point. So even without doing the second derivative, I mean, you understand, you could find the point of inflection. Perfect.
Yeah.
You have already.
So it's good to double check though.
Yes, we'll double check that, right? And we have also got one of the local minimums. Now we know there's another local maximum which we need to find. So definitely first derivative. In any case, we need to understand concavity and so many other things. And therefore, it is very important to, perform all the operations. And so we should follow a particular algorithm to ensure that we have covered each and everything. Correct?
Yeah.
Can you read question number 9 for me and answer that?
Question 9?
Yes.
All right. How many point of inflections do you expect for f of x?
You said 1. Question number
1.
10.
Yeah. Will the first derivative be 0 or undefined at the point of inflection?
Yes.
Will it be? It will be undefined.
Why?
Because we already said that it's going up and then it hits the
concavity changes.
Concavity changes at 2. That's the local minimum, and then it goes up again.
Yeah, we are talking about point of inflection. Now,
yeah, so it'd be
at point of inflection, I mean, it is very important to understand. If I have a cubic function, then the x-axis crosses the point of inflection, where the first derivative is 0 because x-axis is horizontal, correct?
Mm.
If you have a cube root function, in that case, the y-axis may cross the function, right? The tangent line is y-axis, where the point of inflection is on the y-axis, and in that case, the first derivative does not exist or is not defined. It's a vertical line, right? Vertical tangent.
Yeah.
However, most of the cubic functions will be somewhere in between. So the graph is coming down, concave down, and then changing, right? So it's coming down and changing. It could do that at any angle. So the derivative could be anything. So that really means that we should not be judging point of inflection with respect to the first derivative. First derivative does not have any idea about the point of inflection. Doesn't make sense, right? Okay.
Because it's the second derivative, isn't it?
It is the second derivative which gets you this, and that was kind of very important to understand. Is that clear to you, right?
So that's a trick question.
That's a trick. No, you know, even the other questions were very good questions, but you're so well prepared that you got 9 out of 10. Perfect. So that's what we need. And for this 10th question, we'll have to do all the things all over again. So let's begin with the understanding of how to really sketch a polynomial graph. Now, I've given you this function, which is f of x equals to x plus 1 times x minus 2 whole square. So easily, we get all the characteristics of the function as soon as we look at this particular function. So in the algorithm, first part of the algorithm is always the information which you can immediately gather from the equation, correct?
Yeah.
So in this particular case, it is domain and range, you know, all real numbers. The y-intercept, substitute 0, you get 4. The x-intercept, you know those two values, minus 1 and 2. Find the zeros. We have those two zeros, one linear, one quadratic. End behavior, moving from quadrant 3 to quadrant 1. Now we come to the first derivative, its analysis, which is going to tell us about maximum and minimum values, I mean local. And then the second derivative will give us the point of inflection. We'll actually confirm with our, you know, one of our questions answer was it is a value given by Amy, which is minus b by 3. We'll confirm whether it's correct or not. So whenever you're doing polynomials, it is important to find local maximum and minimum along with point of inflection. And that gives you most of the marks. Is that clear to you?
Yeah.
So let's continue to find the first derivative. Now, you could use a product formula, correct? We have two factors, x plus 1 times x minus 2 whole square. Definitely, you can use product formula. But you realize that, you know, it becomes complicated. Why not for once expand, simplify it, correct? So when you expand, simplify, you get this particular expression, which is x cubed minus 3x squared plus 4. Now, to find derivatives, that is a better expression. So simplify such expressions, especially when it is only up to a cubic function. Perfect. Now, the derivative is 3x squared minus 6x, right? So that is your derivative. You can factor out, since we need to find the critical numbers. Critical numbers, or for polynomials, we also say stationary points, since at these points, the derivative is 0. Now, so once you factor, you know, the derivative should be 0 at x equals to 0 and at x equals to 2. Perfect?
Yeah.
But this is also a good time to also find the second derivative. Perfect. So we have second derivative. You could factor that and write it down here itself, right? Now let me summarize the other behaviors or the characteristics which we have recorded. Let's record them. We know that the domain is all real numbers, range is all real numbers, y-intercept is at 4, the x-intercepts are at minus 1 and 2, the zeros. We have order 1 at x equals to minus 1, order 2 at x equals to 2, end behavior. X approaches minus infinity, then y approaches minus infinity. Quadrant 3, x approaches plus infinity, y approaches plus infinity. Quadrant 1, correct? So we have the characteristics, we have the derivatives. Now it is time to analyze them, correct? So let's try to analyze the very first derivative, which for us is, we know the function is x cubed minus 3x squared plus 4, and the derivative we just found in factored form can be written as 3x times x minus 2, which gives us two stationary points, one at x equals to 0, the other one at x equals to 2. So it's always a good idea to also find the values of these x values. So we can always calculate this. We know exactly that the point is 0, 4 and 2, 0, correct?
Mm-hmm.
Okay. But now major thing is to analyze the second, I should have written first derivative. We are doing first derivative. So we have to analyze the first derivative for this particular function, correct?
Mm-hmm.
So let's analyze the derivative with the interval table. Now, I have made the interval table here. Amy, we have used this interval table earlier also. Can you explain me what are we trying to do using this interval table?
Yeah, so we found the zeros. So we just, so the first like row says x equals 0, x equals 2.
Yes.
Now we like use test points.
Yes.
So imagine like a number line. Let's choose really easy points, preferably whole numbers. So -1 on the left side, then you go 1 in between 0 and 2, and 3 after 2.
Perfect.
Then it's in factored form, 3x and x minus 2. So I don't think you're allowed to use calculators. So it's better to use them individually and sub the values in. You don't have to get the actual values. You just need to know if it's negative or positive. So that's why Mr. Kumar has put the signs. So you put minus and then whatever the signs are. Yeah.
Perfect.
And then because they're being multiplied, you multiply down the column. So with -1, both negatives make a positive. A negative and a positive make a negative, and then two positives make a positive.
That is perfect. What do these negative positive function first derivative values indicate?
So arrows are really helpful. So what I do is when there's a positive, you put it as increasing. As you see a negative, you put it as decreasing, and then another negative, so decreasing, and then increasing again. Yeah. So what this shows is you can literally imagine, so as it goes up and then down, we're hitting a maximum point. Yes. So that's why there's a maximum value at x equals to 0. Yes. And then when you're going down and then up again, you're getting that concave up, so minimum value. Yes. So there's a minimum at x equals 2. Perfect.
We'll not use the term concave up yet, because concave up we are going to use only when we do second derivative. All right. The graph of the curve is rising or falling, the gradient we are talking about, correct? Okay. So the graph is falling and hits the minimum, then goes up. So we have a local minimum there. Now we know the values at these 2 points. So we have local maximum at 0, 4 and local minimum at 2, 0. Now, the term local may or may not be used. So when we are talking about polynomials, we know that they are going from one infinity to the other. So definitely anything in between will not be an absolute value of extrema. Is that clear? So we just use the term maximum and minimum, and there could be many maximum and minimums in between. A better way, therefore, is to use local maximum and local minimum. Correct? Okay, so we got our critical points and we have analyzed them. So we have now both local maximum and minimum. Now it's the turn to analyze the second derivative. So let's find the second derivative. Definitely, we're going to use the expression for the first derivative, which is 3x squared minus 6x. So when you do the second derivative, you get 6x minus 6. You can factor out 6 and get x minus 1. The only critical number here is at x equals to 1. So once again, we are going to analyze the second derivative using the interval table. So Amy, can you summarize this particular interval table and explain what are we trying to find?
Yeah, so with second derivative, you always need to remember that it's to do with concavity. So change of concavity and point of inflection. Yes. So nothing to do with maximum minimum, because that's what we already did with the first derivative. Perfect. So you put your point down as x equals 1, and yet again we find 2 test points either side of it. So left side being 0, right side being 2. Then you sub those values into 6 bracket x minus 1, and we get 0 as being negative and 2 as being positive.
Because 2 minus 1 is positive, you get a positive value. 0 minus 1 is negative. You get a negative value.
Yeah.
Then,
And then, so the negative sign tells us that it's concave down,
yes.
and positive sign tells us it's concave up.
Perfect.
So in between that change of concavity from down to up, we have a point of inflection at x equals to 1.
Perfect. So find the value at 1. You know it is 2. A point of inflection is at 1, 2. Done. So we have everything required to sketch the graph now?
Yeah.
Very good. So let's sketch it. So it's a good idea to summarize all our learnings at one place. We know exactly what to do, and then sketch the graph. So Amy, can you read this out and see what is our summary?
Yeah. So sketch the graph of f of x equals x plus 1 bracket x minus 2 whole squared. So we found the y-intercept, which is 0, 4.
Mm-hmm.
X-intercepts at x equals minus 1 and x equals 2. Zeros with order. So at x equals minus 1, the order is 1. And at x equals 2, the order is 2. Yeah, that's why we've got that quadratic curve. End behavior. So as x approaches negative infinity, y approaches negative infinity. As x approaches infinity, y approaches infinity.
Correct.
Yeah.
Maximum, minimum points.
Yeah, so maximum at 0, 4. Minimum at 2, 0.
Yes.
Concave
Point of
down.
inflection. Yeah, concave up all along, right?
Yeah.
This is your concave up portion, correct? After this, I'm sorry. After this, right? And
Yeah.
concave, sorry, concave down is this. Perfect. Okay. Yes, Amy, can you tell me about concavity?
Right. Concave down. So that would be from minus infinity to 1. Yeah.
Yes.
And concave up from 1 to infinity.
Perfect. And point of inflection?
At 0.12.
Now, does your calculation shows that this should be your answer? So let's get back to our equation itself in this form, right? So minus b means 3, correct? Divide by 3. So 3 divided by 3 is 1. And so we have point of inflection at x equals to 1. Does it make sense?
Yeah.
So it's perfect. So whatever we decided or we thought about it, it just came true. And therefore, we have exactly, what we thought about. And we got the values also as expected. Now, it's a good idea to actually, when you look at the question, you should think about it and then go about solving it. Because as you solve, you're confirming to your thinking, and it is a good practice, right? You know you're on the right track. Does it make sense to you, right? Now, let me emphasize at this particular case, in the books, we really emphasize on algorithms, right? Every book. And even teachers will say, well, in our algorithm, you did not follow step number 4, and so 0.5 gone. But I think it's all not required. Because algorithm is a means of getting to something. You should have flexibility to use it as it should be used, correct? Now let's take another
It's quite
function.
a lot of steps.
Yes,
quite
it's common sense. It is common sense, right? So you can begin from anywhere. Polynomials, we thought domain, range, x-intercept, y-intercept, easy values, pick them up, end behavior, right? And then the calculation part was really to find the derivatives and analyzing them. Perfect.
Yeah.
Do simple things first, and then get into complex cases of calculating some values and putting them on the graph for being it extremely accurate. And that's why we are saying graph the polynomial. We are not saying sketch the polynomial, right?
Yeah.
Now, example 2 is rational function. We need to sketch graph of f of x, which is x squared minus 3x plus 6 divided by x minus 1. Do not determine the second derivative. We are given this as a part of question itself so that students may not spend a lot of time in finding the second derivative. Second derivative of this particular function could be very tricky and time consuming, right? And why do you think it has been included in the question, do not determine the second derivative? Amy, can you answer this question?
Is it because after you do all the algorithm that you've listed
Yeah.
is not really necessary. It will just confirm that what you've done is like right, because
That is
it
true.
gives everything. Yeah.
We don't expect a point of inflection in this particular case for rational function. So most of the time in a rational function, you should remember there will not be a point of inflection most of the time. Okay.
Oh.
Yeah, unless and until we'll have some cubic term involved. So if there is a cubic term involved, there will be, but not otherwise. Is that clear?
Oh, that makes sense.
So
Yeah.
yeah. So in examination, it is very important to understand what to do and what not to do. You might spend about 10 minutes finding the second derivative and then coming up with the result that there is no point of inflection. But it'll be sheer waste of your time in an examination hall. Okay? So remember this part. We have specifically mentioned do not determine the second derivative. It is here for a reason. Okay? Now, when we are talking about rational functions, what is more important for us? It is the asymptotes which are more important when we are talking about rational functions, correct?
Yeah.
When we were talking about polynomials, did we talk about asymptotes?
No.
It makes no sense. Perfect?
Yeah.
Now, if I have to write an algorithm for sketching graphs of functions, I will definitely include that chapter of asymptotes in between because it is a part of algorithm, right? But as you have seen, this part of algorithm about finding asymptotes and behavior near the asymptotes is irrelevant for a polynomial function.
Yeah.
Therefore, when we have about 15-step algorithm, we should know exactly which steps are redundant, which should be avoided. Perfect?
Yeah.
So, when we did polynomials, we simply skipped the part which was dealing with asymptotes. Now, when we are doing rational functions, we'll skip the part, the second derivative. You see that part? So, so look at your algorithm as a means of helping you find a solution, and you should be smart enough to choose the right thing from that list. Is that clear?
That makes sense, yeah.
Yeah. Now, I've mentioned these units, algorithm for curve sketching. Emmy, can you read this for me?
Yeah. So vertical asymptote, horizontal asymptote, oblique asymptote, domain and range, find Y-intercepts, find X-intercepts, find first derivative, and analyzed first derivative for extrema.
Correct. Here I have another note, which is this particular thing, find X-intercept. Finding X-intercept means you will equate the function to 0, Y value, and then you will equate the numerator to 0. That is your X-intercept, right?
Yeah.
So in this particular case, it is not very difficult. You could straight away apply quadratic formula, get your X-intercepts, right? However, if you have a rational function of degree more than 2, maybe 3 also, do not find X-intercepts. You can make a note because it's very complicated. It is like solving a cubic equation, which is not so easy. You don't have a quadratic type formula there, correct?
That's true.
The idea is to sketch a graph at this instance, not to solve an equation. And therefore, this particular find X-intercept should be treated with caution. You should, most of the time, skip it if it is difficult or time consuming. It is not a critical part of curve sketching. Is that clear?
Yeah, so if the top of the numerator can be easily like factored, then do it.
Then do it. Otherwise not. Okay?
Yeah.
Otherwise not. So so that is important to understand. Now let's begin with the characteristics of this particular function. Now here, it is important to find the asymptotes and behavior near asymptotes, and that will fetch you most of the marks. Is that clear?
Yeah.
So let's look into the function itself. Now, some more questions for you. Amy, can you read from question number 1 and answer?
Right. So what is domain of f of x? Is it x cannot be equal to 1?
And all other real numbers. This is what you're going to say. Perfect.
What is range of f of x?
Yeah.
What do you need to answer this question?
This is a very difficult question to answer at the moment. We really need to work on it, okay? Because this function will have a local minimum, this function will have a local maximum, and in between it may not have anything, right? So
All right.
range will be very much restricted. So we cannot really answer this question at the moment. Is that clear?
Yeah.
Which asymptote do you expect for f of x? Apart from, okay, yeah, which asymptotes do you expect? Tell me.
Vertical asymptote
And
at x equals to 1, and oblique asymptote.
why oblique?
Because the degree is one higher than the numerator degree is one higher than the
Good job.
denominator.
Good job. So that is perfect, right? So that's correct. And how will you find the number of x-intercepts for this particular function? Number of x-intercepts. You have a quadratic function on the top, b square minus 4ac will give you a number of x-intercept. So you could use quadratic formula and find the real values of zeros, correct? So in this particular case, b value is 3. 3 square is 9. 9 minus 4ac means 4 times 6 is 24. 9 minus 24 is a negative number. So within the square root, we have a negative number, and therefore we have no x-intercepts. Do you get the idea?
Yeah.
Got it?
Yeah, yeah.
Good idea to check the x-intercepts in this particular point. You know that the graph is not reaching the x-axis or crossing it at all. You see that? Because there are no real values for x-intercept. That also gives you a clue that y equals to 0 is definitely out of range, right?
Yeah.
And therefore, I was saying this function will have a local minimum and a local maximum, and in between values are missing. And therefore, it's not very easy to answer the range question at the moment. Is that clear?
Yeah.
Next question. 5.
What is the y-intercept of f of x?
Tell me this.
So would you... Why do I feel like it's a trick question?
No, just put x equals to 0.
Oh, just put x, okay. Then that'll be
X equals to
6
0, what do you get?
minus 6.
Perfect. So that
0
is the
minus
y-intercept, easy value, right? So don't lose these easy values. Mark them on the graph paper as you get these values.
All right, okay.
Question 6.
Y second derivative may not be critical to sketch the graph of f of x. So we said, oh no, we didn't say, may not be critical.
Yeah, may not be critical. We are not going to find second derivative because there are no point of inflection. No point of inflection, no point doing it. Is that okay?
Yeah, that makes sense.
Yes.
What happens to the curve of f of x when x approaches very large positive value?
Yes, tell me.
It would be above the oblique asymptote.
Okay, you gave an answer above the oblique asymptote. Very difficult to provide this answer now, but definitely it is approaching the oblique asymptote. Is that okay?
All right. Okay.
Yeah, it is approaching the oblique asymptote. When you write a very high value for x here, then in that case, you may get a clue that it is actually approaching from above, right? But it is approaching the oblique asymptote. And by definition, that is what oblique asymptote is. Since the degree of numerator is 1 higher, we expect oblique asymptote. The function, when approaching negative or positive infinity, may be approaching this oblique asymptote from above or below, right? We'll analyze it first. Now let's look into oblique asymptote, because we know that the vertical asymptote is at x equals to 1. Okay, so now we know from here that the vertical asymptote is at x equals to 1. Perfect. Do we have a horizontal asymptote? Not at all, because you can have only one of these, horizontal or oblique. Horizontal asymptote you get when the degrees of numerator and denominator are either same or the degree of numerator is lower. Oblique asymptote you get when the degree is 1 higher for the numerator, correct? Behavior near asymptotes is what we need to figure out. We have found one value, which is the y-intercept, and we're just trying to do all this. So now let's analyze the asymptote. To analyze the asymptote, first step is we have to find our asymptote. We're talking about the oblique asymptote first, right? Okay, that's a difficult part. So here I have done synthetic division. You remember synthetic division, right?
Yeah.
Okay. So the numerator is x squared minus 3x plus 6. We have written the coefficients 1, minus 3, and plus 6. We're dividing by what makes the denominator 0, which is 1. And how do we do it? We bring the first term down as such, multiply by the dividend, divisor, which is 1, and write the product here. Then again, we add minus 3 and 1, we get minus 2, multiply by 1, write it there. And then again, we add and get a remainder. Now, for those students who are not very clear about synthetic division, you could perform long division, correct? Dividing the numerator by denominator will give you quotient as x minus 2, remainder 4, which remains to be still divided by x minus 1. Correct? Think like this.
Yeah.
And so we could write the function in the form shown here, x minus 2 plus 4 over x minus 1. So clearly, we have oblique asymptote whose equation is x minus 2. So this line L is the oblique asymptote. Now, let's try to understand the behavior near the asymptote. Let's go with the positive value first. So if I write a very large positive value, in that case, to the line x minus 2, we have to add something, right? 4 over a positive value means we have to add something, correct?
Yeah.
So our function is above the line. You get the idea? Above the line. So we are approaching from above. Now, if I change this x to a negative value, this plus becomes a negative value, correct? So it hits below the line. Do you understand now? So that is how we see when x is approaching negative infinity, the graph of the function approaches the oblique asymptote below the line. But when we are approaching on the positive side, it is approaching above the line. Is that clear to you?
Yeah. So you're saying the way to know if it's above or below the line, you just sub in x minus infinity and positive infinity into the function.
Minus infinity really means a value like 1,000, right?
Oh,
so just use calculator, write 1,000, or even 100 in this case, 100 times 1 or 2. These numbers are small numbers. So normally you can use 100 also, but 1,000 is preferred value. Plus 1,000 and minus 1,000. It is as good as plus and minus infinity for the numbers given, which are like 1, 3, 6 and all, correct?
That's quite easy.
So we have done the difficult part first, that was analyzing the oblique asymptote. Now, simple part is to analyze the vertical asymptote, which is at x equals to 1. So when you are approaching 1 from the left side, in that case, you will notice in the function that the y value approaches minus infinity. So approaching from the left side really means use your calculator and substitute 0.9, right? 0.9 means approaching from left for 1. And when you substitute 1.1, we are approaching 1 from the right side, correct? 1.1 is from the right side. And you will see you get a positive value. So if you get positive value, that means you are approaching positive infinity. Is that clear?
Right.
So use your calculator to find the solution rather than substituting or analyzing the given equation. So make a note of this.
Yeah.
Perfect. Now you got oblique asymptote and the vertical asymptote. We are in good position to find the first derivative and analyze, since we understand that the graph actually is moving from minus infinity to plus infinity. However, it is not crossing the x-axis. That means in between it is turning somewhere, correct? So it becomes critical for us to find the first derivative. Now, to find the first derivative, we need to use the quotient rule. Remember, x is not equal to 1. That is the restriction on this particular function. And that restriction will always remain a critical point also. So always include that into your table of, checking this particular thing. It's very important. Right? Sometimes students might just miss it, but this cannot be missed. Now, when you find the first derivative, that means you have to write the square of the denominator, first thing. Then numerator derivative. So derivative of the numerator is 2x minus 3 times the denominator minus derivative of denominator, which is just 1. I didn't write. 1 means 1 times anything is the same thing, and the function numerator, which is x squared minus 3x plus 6. Now
Yeah.
you combine the terms, simplify, and write it in factored form. Once you write it in factored form, it is very easy to find the critical number. Perfect.
Mm-hmm.
Do you appreciate that we use the term critical number here and not the stationary number or a stationary point? Can you tell me why?
Because critical number is where the f prime x either equals 0 or is undefined.
Yes, or does not exist. But the
Yeah.
stationary point is a point where it is 0, right?
Only,
So
yeah.
when we talk about a stationary point, we are not talking about the condition that the first derivative is undefined or does not exist. Is it clear?
Mm.
But whenever we are talking about rational functions, the critical number will include a point where the derivative does not exist. Is it okay?
Yeah.
So use the term critical number, and definitely we have 3 of them, 3 factors, correct? 2 in numerator, which are giving you zeros. So these zeros, which are at -1 and 3, can be included in your solution because they are zeros, right?
Mm.
And then we have a vertical asymptote 1, should not be included in your solution. This is not a part of domain. These 3 points divide the whole plane into 4 intervals. And now we'll again utilize the technique of our table to analyze in which region the function first derivative or the gradient is positive and negative. So Amy, can you explain me this particular table of analyzing the first derivative, please?
Yeah. So we place the critical numbers at the top. So -1, 1, and 3. Then you choose test points like before. So we do on the left side of -1, so just -2. Between -1 and 1, we chose 0. Between 1 and 3, we chose 2. And 3 to infinity, just choose like 4.
Okay.
Then you sub in those test points into, so we broke down the derivative into x minus 1 squared, whole squared, x plus 1 and x minus 3. Do them individually, yep. And then sub those test points into the equations, and we get the values. So either if it's positive, so for example, -2 minus 1 is -3, but anything squared would be positive. That's why the whole row is positive.
Perfect.
Then you sub in -2 plus 1 is -1. So we got negative and so on. So we get all our points. And because they're being so the top is getting multiplied.
All 3 are multiplied.
No, all 3 are getting multiplied, sorry. So positive multiplied by 2 negatives give us a positive. So we have an increasing arrow. 2 positives multiplied by 2.
Negatives.
No, 1 negative is a negative. So we've got decreasing, and 2 positive, and the same thing. Yeah.
Yes.
So
that is great. Yeah. So now what Amy, you're saying is we should be actually looking only for negatives. If we have even number of negatives, it will result into positive.
Positive.
If you have odd number of negatives, it will result into negative. Simple as that. Is that clear?
Yeah.
And if you get the gradient as positive, mark arrow increasing. If the gradient is negative, mark arrow decreasing. Now from here, what do you infer?
So when we see it going from increasing to decreasing, we have hit a local maximum.
Yes.
So we know there's a maximum at x equals -1.
Yes.
And from 1 to 3, we've got a decreasing to increasing. So we've hit a local minimum. So we know there's a local minimum at x equals to 3.
Perfect.
To find the y values, you just sub those x values into the function. Yeah.
Correct. And get the values. And nothing at 1, correct? Even if this would have been going up or down, you cannot include 1 in your solution. Remember that. Since that is a vertical asymptote, it's not a part of your domain. Is that clear?
Yeah.
Okay. Now coming back to this particular table, many times I've seen this table shown in 2 different ways, and that's the reason why. I have also showed the table in two different ways. Now I'll tell you how. This is the preferred thing. So let me just say this is the right way of putting it. Now the wrong way of putting it is, earlier I have shown somewhere, yes. I will say this is not so right. I'll say like question mark. Now when you look at this particular part here, you see that x equals to 0, I wrote here, and also x equals to 2. In between, there is a gap. You see that portion, right?
Yeah.
And this two arrows going down gives us kind of a like confusion. What is happening here, right?
Yeah.
So this is not a good way of doing it. So if you really want to show these points and the test points, the correct way is as we have done right here. Do you see this portion?
All
Now there
right.
is no confusion, right? So what we are doing here is we are writing each point above, and then left and right of those we are taking the test points. Do you see that?
Could I take a picture?
Take a picture. Left and right of these points we are taking our test points, and then the arrows create no confusion. Now again we do have two arrows coming down. We know clearly that at one we have neither. You get the idea, right? So I purposely done so because many places I've seen the other convention being followed throughout the books, but kind of it creates confusion. Okay, so is that clear, Amy?
Yeah. So that's the better layout.
That is the best. Now you have to summarize everything and plot the graph, correct? So it's kind of very important to write down summary of whatever you've done. This is the summary where there's a typing error. I just saw it. Y-intercept is -6, not +6. Correct? -6, right?
Yeah. Because it's 6 divided by
-1. Correct. So that's a typing error. So anyway, so what you see here is an oblique asymptote right there, and this oblique asymptote is y equals to x minus 2. Correct? So that is the equation. So it has y-intercept, and that orange line dotted shows oblique asymptote. And we can see that the graph of the function approaches from top while approaching positive infinity, or negative infinity, it approaches from bottom. And we have a vertical asymptote at x equals to 1. Perfect. And the points which are local maximum and local minimum are also marked, correct?
Yeah.
Now, Amy, you can write the range of the function. Perfect. What is the range of this particular function?
So y belongs to real numbers.
Yes.
Where y is between x being, wait, so that's 1, 2.
Yeah. So maximum is at -1, -5. So the y value is less than equal to -5, correct?
Yeah, and less than equal to 3.
And greater than equal to 3 on the other side. Is that
and then,
that is the most tricky part of this particular question. So once you find your local maximum minimum, sketch it, then the things are very clear that the range of this function is y is from -infinity to -5, where -5 is included, the square bracket, and on the right side square bracket 3 and a circle, open bracket of infinity, right? So that is the range of this particular function. Is it clear?
Yeah, could you just write that like down? Do you write it individually or do you write it as like one?
Union. Okay, so we write it like this. We say y equals to, the range equals to, y belongs to real numbers such that, which is a straight line, correct? And then you write two inequalities. The first one is y is less than equal to -5, right? Union or. So you write y is less than equal to -5, correct? Or write union, u, right? And then you say y is greater than equal to 3. Is that clear?
Yeah.
My screen is vertical, so very difficult to write on a vertical screen like this with less space. Okay, is that clear?
That makes sense, yeah.
That is the part which will end here, And here, of course, to say y belongs to real
Real
numbers,
numbers.
and that is the bracket. Is that clear?
Yeah.
So you have to split it in two and then write as shown here, right? Now let's take
If
the,
you write it,
yes,
sorry, if you write it as 1, is that wrong?
you cannot write. That will be absolutely wrong way of writing, okay? Never.
Okay.
When you write together, all the arrows have to face the same side. So you could write sometimes when you do parabola that the value of x is in between -2 and +2. All arrows are facing the same side. Is that clear to you?
Yeah.
But you cannot combine the opposite arrows in the one side.
Right.
You have to split it as shown here, right? So you could use the word or also in this particular case, right? Or union. You could use or also. It's one and the same thing. Perfect? Okay, now let's continue. The last example here is based on thirds. So in examination, we have seen most of the time, they will be asking polynomials and rational functions in different ways for simple, increasing, decreasing interval, concavity, and point of inflection. But when they give you a graph to sketch, then this will be the kind of function before you. I've actually taken a very simple, rather simplest of all the cases because I wanted to give a difficult one for a test, right? That's what teachers do, right? We always take very simple examples. So here is a very simple example. F of x equals to x to the power of 5 over 2 minus 10 times x over power is 3 over 2. Now, when you're looking at two asserts or radical functions, in that case, domain is kind of very important since the domain is restricted, right? Most of the square root, we cannot have negative numbers, something positive, right? So that gives you one end or the boundary of our function. Now, when you get something at the boundary, at that particular point, we cannot analyze from both the sides because it is just one end of it, correct?
Oh, yeah.
We were analyzing the first and second derivative from both the sides, but now we cannot. So this point, whichever is the end point, which seems to be 0 in this particular equation, can only be analyzed from the right-hand side, not from the left-hand side. Is that clear?
Yeah.
So keep that in mind. Now, simple questions like, what is the y-intercept? You can calculate. Some values like x equals to 0, x equals to 0, you can calculate, right? X equals to 1, x equals to 1, you can calculate. These are good values to calculate. They give you more accuracy. So whatever good values you can find for thirds, calculate and put them on side because you can always put them on the graph, right?
Yeah.
You may not have them as a critical point or a critical number, correct?
Yeah.
Okay, so evaluate these values, and that is why I've mentioned this, evaluate f of 1. Look for such values. Is that clear?
Yeah.
Okay, so for example, when we do square root, we know square root of 4 is 2, right? And the other thing is power. We could calculate the function's value at 4 also. It helps. It helps.
Okay.
Now, question number 4 here is, how will you find the number of x-intercepts of f of x? Tell me this.
X-intercepts.
Yes.
So you make y equal to 0.
Yes. And then solve. How will you solve?
First derivative?
First.
Oh, no.
Factor. Just factor. So, yeah, just factor it out. And, the lower one is 3 by 2. So you factor x 3 by 2, and then whatever remains inside remains. You have two factors. X equals to 0 is one of your zeros. And when you factor x to the power of 3 over 2, you'll get just the value x here and minus 10 there. And so you know the other 0 is at 10. It's not very difficult, right? So you can easily find x-intercepts by factoring, right? Now, can the function have absolute maximum minimum? Yes. These functions can have absolute maximum minimum. That means the range of the function may be restricted, right?
Yeah.
Is second derivative important for this function? Yes. So whenever we have a turning points like this, for a radical function, second derivative is very important. it is difficult to find. However, you cannot avoid it. You get my point?
Yeah.
So remember, in rational function, you could avoid it, but in radical functions, you cannot.
Okay.
And it's very difficult, right?
Yeah.
So get ready for this.
You need to remember all these rules.
Yes.
Just like which ones need to use second, which ones don't.
Yes.
Yeah, because it helps.
You cannot avoid second derivative. It may be difficult, but that's half the marks, right? Okay, so we'll see how to sketch this particular function, which is f of x equals to x to the power of 5 over 2 minus 10 times x to the power 3 over 2. So you will see I have not really getting into algorithm now. We have been talking about algorithm. We have concept in our mind. We'll work with the concept, right? Algorithm helps us to derive at a good result. Perfect. So easy values, f equals to 0, I just calculated. F equals to 1, I calculated. It is not given in any algorithm. But these are easy values. I could add f equals to 4 also and calculate one more point.
Yeah.
So you could do that. Now, second thing, we need to factor this to get the x-intercepts. So I factored x to the power of 3 over 2, getting x minus 10 as the other factor. It gives me two x-intercepts, one at 0, the other one as 10. Is that clear?
Yeah.
So we got two zeros. Now, you can mark these things on your graph paper, all the things 4 points already, correct? Now, get into the difficult stuff of finding the derivative of these radicals. So when you do the derivative, you can use each term. So just power rule can work for you. So you get 5 over 2, x to the power of 5 over 2 minus 1, which is half, right?
Yeah.
And you get 3 by 2, I'm sorry, which is 3 by 2. And then you do 3 by 2 and x 3 by 2 minus 1, which is half. So you get the other derivative. Then you factor. Since we need to analyze the first derivative, you have to factor. And you get two zeros or two critical numbers. One at x equals to 0, the other one at x equals to 6. So at these critical numbers, we'll analyze using our table. Correct?
Yeah.
So in this particular case, fortunately for us, the exponents are not negative. So I've used the term stationary points. But normally, we'll use critical points. Is that clear?
Yeah.
Now in GCSE, I've seen most of the examples, because they stick with the term stationary points, you are actually lucky, Amy, that most of the time you will not get critical points.
Oh, right.
Because they will not like to contradict what they have been saying so far, correct?
Oh, okay.
So that's a good thing. And this type of example should be there in your test paper, but not in most of the test papers, okay?
Oh, okay.
So when we talk about thirds in Canada or anywhere else, we'll have definitely the exponents, which will result into negative values as the exponent. And so we'll have a critical point where the denominator equals to 0 needs to be analyzed. Is that clear?
Yeah.
So that gives you kind of a, safe, and, it's a hint that in your case, most of the time it is stationary points. Is that clear? And now you can analyze the first derivative as we had been doing. So clearly, what I've done here is that I've written x equals to 0 and x equals to 6. And on the left side of x equals to 0, I'm not taking any point to analyze, since that is not a part of our domain.
Yeah.
We figured out that the domain here is x greater than equal to 0. Is that clear to you? Right?
Yeah.
Now, once it is clear, we'll take the test points on either side of 6, which one of them is between 0 and 6 also. And we'll follow the same method as we did in the previous examples. And we know the signs. And working out on the signs, we know the sign of the first derivative. Since the first derivative changes from negative to positive, we know we hit a minimum at x equals to 6. So plug in 6 and find your point. So f of 6, use calculator to get this particular point. We have this minimum point with us. Is that clear?
Yeah.
Now, once you have the first derivative, use this form, which is not a factored form, to find the second derivative, right? So let's move on. We have the first derivative in standard form, not the factored form, correct? From here, find the second derivative, but factor the second derivative to analyze. And again, we get two critical numbers. Which ones are at 0 and 2, right?
Mhm.
So now again, we'll take test points of this particular 0 and 2. Only on the right side of 0 we have taken, since the left side is not in our domain. So don't use -1, okay?
All right.
Yep. So for 2, we have 2 points, one on the left, x equals to 1, one on the right, x equals to 3. And we find positive or negative. If the result is negative, then the graph is concave down. If the result is positive, the graph is concave up. Perfect?
Perfect.
That's what we do. Well, as a habit, I'm using critical number. You may use stationary point in this particular case. Okay?
No, I'm used to using critical number now.
Very
I
good.
like
Very
it.
good.
Yeah.
It's a safe bet, right? Believe me,
Yeah.
using critical number is better. Now, since we found that we have a point of inflection at x equals to 2, substitute and find the decimal value, right?
Mhm.
3 significant figures is minimum. 3 significant figures. Remember,
Oh,
we are
okay.
never writing in our questions like to what accuracy, but by default, it is 3 significant figures. Is that clear? So make a
All
note
right.
of this. That is the default accuracy, okay? Now we have everything. So let's sketch this particular graph. Summarize all your learnings, right, as done here on this page, correct? Can you read this summary and explain me the graph, please, Emmy?
Yeah. So summary of the key parameters. So domain of f of x equals x belongs to real numbers where x is greater than or equal to 0.
Yes,
So like in the beginning, we said that the domain is restricted.
yes,
So there won't be, we're not coming from the left side. So that's why you can see it's only from the right.
correct.
Then range, y belongs to real numbers where y is greater than or equal to minus 58.8, which we
Correct.
found is the minimum point. X-intercept at x equals 0 and x equals 10.
Yes,
Decreasing interval from 0 to 6. Increasing interval from 6 to infinity.
correct.
Local minimum at 6 minus 58.8.
Correct.
Concave down between 0 and 2.
Only this much. Yes.
Yeah. Concave up between 2 and infinity.
Correct.
And point of inflection at 2 minus 22.6.
Correct. So these are the features which are very important features to list as the properties of this particular function. Is that clear to you? So
Yeah.
I have not really mentioned them as a part of the question. However, the question was only to sketch the graph. Graph is there before us. You could have many related questions. What is the interval of increasing? What is the interval of decreasing? What is the interval for concavity? So that is how you have to answer those related questions. Is that clear?
That's clear.
So when we are doing curve sketching, we are answering 101 questions, everything which we have learned so far. Do you see that part?
Yeah.
So it's kind of a good refresh at this moment to understand what all we have learned about. And there we go. And after this, we are going to take up further derivatives using more complex ones, using chain rule and implicit differentiation. Perfect. Now here are a few questions for you. You can take a picture of these questions, Emmy. And I also provide the link of my videos which have solution for these particular graphs. So I thought that I'll give you a difficult question to work with, which will give you good practice to really take examination style question based on certs. Is that clear to you?
Okay. Yeah.
So critical number will be critical here. Okay. Now we have two rational functions. I have not taken polynomials since we have done a lot of practice with polynomials so far. Is that clear?
Yeah.
So work with rational functions. They could have oblique asymptotes. They may have horizontal asymptotes. So basically, on that basis, I have taken these two questions. They should give you good practice, and then we can actually move forward. Is that clear?
Mm. Just quick question. With
Yep.
the rational functions, would the general shape of it be like 1 over x kind of thing?
Yes.
Okay.
1 over x is the normal shape when you have a combination of horizontal and vertical asymptote.
Okay.
Is that clear?
Just so I know I'm on the right line.
Yes, yes. But if you have oblique asymptote, then that is the shape.
Oh, okay.
You get the idea?
Okay.
Well, I'll send you one more example where we may have a cubic function. So cubic roots, are kind of like this, right? So that will go through and through the asymptote, right? And that may have a different shape. That's what I'm trying to say.
Right.
Correct?
Yeah.
So you need to do an example on cubic function. I'll send you that. That should give you the shapes taken care of. Is that clear to you?
Yeah.
Right? So now, Amy, it's time for you to summarize what we have learned today.
Right. So we started off. So we're sketching graphs of curves. We started off with the basic polynomial, and we have algorithms, which there are so many, like more than 10 or 10, let's say, algorithms. But according to what the function is, whether it's a polynomial, whether it's a rational function, whether it was a radical function, you need to know, after watching this video, you would know which one of those algorithms to choose, so that you don't waste time doing one that would just end up with a dead end. So you have to choose them wisely and pick them. Obviously, the normal ones would be finding, so with polynomial, we always start with finding the degree, zeros, order, Y-intercepts, and things. When it's rational functions, it's always to do with the asymptotes. So it will be a vertical asymptote, horizontal or oblique. You can only have one or the other. And finding the asymptotes would just generally help you sketch the curve. That's pretty much all you need. And then along come with the intercepts. And then the radical one, just find, now when you choose nice test points, it's always good to use 0 and 1 because you can easily find the values. And if it's like 3/2 or something, choosing numbers that would easily be square rooted are good points to pick. And yeah, using first derivative and second derivative. First derivative finding the local maximum and minimum, and second derivative finding the concavity and point of inflection.
Perfect.
And you got your whole curve.
Perfect. That's great. That's great. So I think you got the complete concept. Try to do these questions, and wherever you have some difficulty, post me so that I can provide you with the required help. And I hope you are in position to solve all the questions in your book in the topics we have covered so far. Now get ready for the chain rule and the implicit differentiation, which we are going to take in our next meeting. Perfect?
Cool. Thank you so much, sir.
So,
I'm actually so happy. Thank you.
Thanks. Bye.
Have a good rest of your day.
You too. Bye. Thank you.
Bye.